Welcome to the physics class for November the 24th. Before we talk about last night's homework, let's go over a couple really important announcements. Okay, so first off, the homework that is due today is homework 7C. I am not going to give a quiz for that homework. So all of the quizzes that are going to be given have been given. And also I have gone back and unlocked all of the quizzes from chapters 6 and 7. You guys hopefully know that all quiz retakes have to be done before we take the test. Well, next time we meet, that will be the test day. Today is just pure review. We're going to do just nothing but review all day long today. And then next time we meet, which for those of you that are in the 8A class will be Monday, even though today is a Monday, and so the next school day you would think should be a B day, for whatever reason, Granite decided they wanted to have 2 B days in a row and then 2 A days in a row. So on if you're in the 8A class, make sure you come here on Monday. And if you're in the B day class and you're watching the recording, then for you the test will be on Tuesday. So all quiz retakes and also all late homework assignments must be done before class starts on the day of the test. So all of the quizzes have been unlocked. You can now go back and retake them as many times as you want until you get a perfect score. Now, when you get that perfect score and I transfer that from Canvas into Aspire, I'm not going to transfer it in as a 10. I'm going to transfer it as a 9. Because if you want to get a 10, you have to get a perfect score before the deadline occurs, which has now passed. Okay, let's see. Oh, tutoring. So you know that there's tutoring every Tuesday, Thursday, and Friday. That's the regular schedule. Except because of Thanksgiving this week, Mr. Wilson has canceled all tutoring. I initially thought he was only going to cancel the Thursday, Friday tutoring, but turns out he canceled the Tuesday tutoring as well, which might be a problem for some of you because I know that with the test happening next time we meet, some of you might appreciate a little extra tutoring time. So what I'm going to do is today, Tuesday, right after the normal school period ends, so starting about 3:45 and running till 5 o'clock, I'm going to do a special tutoring session right here in this Zoom room. Don't go to the normal tutoring Zoom room. Come here to the same room that you're in right now, and I will be here this afternoon from 3:45 until 5. And also one of the tutors is also going to be here with me. So if necessary, we can break up into 2 different breakout rooms. If some of you have questions about one thing and others of you have questions about other things, we can do that. So that'll be today after school. Take advantage of that. And then this coming Friday, there's not going to be any tutoring, and I'm not going to do office hours on Friday either. So it's today or nothing. And then the test. Okay, so I'm going to run the test the same way that I've run all of my previous tests. So they will be taken on Canvas. There will only be one part to the test. You are allowed to use your notes. You're even allowed to open up the book and use the book. You're even allowed to go on the internet and search stuff on the internet if you want. But I don't recommend that, because if you have to waste time doing that, then you're not going to finish the test in the allotted time. So have a cheat sheet ready to go. Have all the important information on that one cheat sheet, so that way you don't have to waste time. Now, it will, of course, be illegal for you to ask another person for help. So you can use any resource that you want as long as that's a non-human resource. Okay, I think that's it for the general announcements. Any questions that you guys can think of that I didn't cover? Okay, well, let's launch into the homework from last night. So here are the answers to, I think it's all of the problems. I don't think any of last night's homework problems had answers in the back of the book. So here they are. As usual, if you could only see one problem done, one problem worked through, what would that one problem be? So vote in the chat box here like normal. Now I'm hoping that I'll have time to do 2 problems, especially because we're not going to do any new material today. So I think I will, but let's see. All right, so I'm seeing votes for 15 and for 94, which is pretty much the same as the other classes. They had the same questions. So I think we can do both. We can do both 15 and 34. So let's jump into 15 first. So take a good quick look at this, maybe even take a screenshot of it if you need. I'm going to open up a new whiteboard for problem 15 here. All right, so what we had in this problem was they wanted us to calculate what is the magnitude of the G field, so the gravitational acceleration field. They wanted us to calculate what is the magnitude of the field not at the Earth's surface, but at some distance away from the Earth, and that distance is the same distance that the moon is at. So if you're at the surface of the Earth, you're going to get 9.8. The higher up you go, the less the number is going to be. So if you go all the way out to the distance of the moon, you can bet that that acceleration due to gravity is going to be a really small number, but not 0. All right, and then also they want you to do the same thing. If you were located at where the moon is, they want to know also what is the G field that you would feel from the presence of the sun. All right, so the way we're going to do this is first off, draw a picture. That's my all-time favorite problem-solving strategy. So there's the sun, here's the Earth, and here is the moon. So they've drawn the picture there, so they want the moon to be located in this particular position here, is 3/4. So if you were to look at the moon right now, you'd see half of the moon illuminated. All right, so the way that we do this is first off, let's ignore the sun. Let's pretend that the sun isn't there, and the only 2 objects in the universe are the moon and the Earth. And in fact, we don't even really need the moon to be there, because if you're calculating the G field, all you need to worry about is the mass of the object that you are near. You don't worry about your own mass. All right, so hopefully from the homework, you know that the way that you calculate the magnitude of the G field is, so little g is what we use for the acceleration due to gravity at any point, and that's what we call the magnitude of the G field. So that's equal to big G, which is the universal gravitational constant, times the mass of whatever planet you happen to be close to, and divided by the distance squared, where the distance is from the center of the planet to where you are. So notice the mass of the moon doesn't come into play here at all. All right, so what number? So we're going to do this for the Earth first, and then we'll come back separately and we'll do it for the sun. All right, so what number do you put in for G? Well, hopefully by now you guys have done so many problems that you know that the number by heart. So 6.67 times 10 to the negative 11th, assuming that all of the other numbers are in standard physics units. All right, so we also need to know what is the mass of the Earth, and we also need to know what is the distance from the Earth to the moon. Now, there's a lot of places where we can get that. Actually, I think, do they even give it to us? Okay, yeah, they give us the numbers in the problem. But if I were to do this on the test, I might not give you the numbers on the test. And so let's pretend that they didn't give us the numbers in the problem. So where would you look to see this? Well, in the back of your book is the graph that I want you guys to practice using. When I gave the test on chapters 6 and 7 in previous years, what I did was I made a photocopy of this chart and I gave that to the students. And so I want you guys to get used to this chart. And it does take a little getting used to, because there's 2 things about this chart that if I had made the chart, I would have done differently. Okay, so one of the things about the chart that I would have done differently if it had been me is that the distances here, they're all given in kilometers. And a kilometer is not a standard physics unit. So anytime you go plugging numbers into an equation that has big G in it, you must, absolutely must, use meters, not kilometers. And so this has caused students problems in the past. All right. And so the second thing is that if you look on the table and you're trying to find the average distance of a planet from the sun or the average distance of the moon from the earth, they don't list it as average distance. What are they listed as? Semi-major axis. Okay. All right, so for this problem that we're working on right now, we need to know what is the average distance of the moon from the earth. So if we look in there, we get semi-major axis of that, and it's in kilometers. So what we need to do is we need to say 0.3844, and notice it's times 10 to the, let's see, let me put on my glasses here. Okay, that's a 6, but that's kilometers. If we're going to go putting this into an equation that's got big G in it, that needs to be meters. So what we need to do is we need to multiply that by 10 to the third meters per kilometers. So that 10 to the 6th now becomes a 10 to the 9th. So what we do is we write it as times 10 to the 9th meters. So that is the number we're going to stick in there. And hopefully that agrees with the number that they gave you. Okay. Yeah, so they rounded it off to 2 sig figs, but yeah, actually they rounded it up. Why did they round it up? They should have rounded it down. They should have rounded it down to 3.8. Oh, that's odd. Okay. And so the other thing we need to know is the mass of the Earth. So if we look up here, there's the mass of the Earth, and notice that is times 10 to the 24th, I believe. Yep, okay, 24th. All right. So even though they gave you the problem, they gave you these numbers in the problem statement, make sure that you guys know how to use this chart. Because when you take the test next week, I might ask you stuff where you're going to need to look in this chart in order to get the information. Make sure you know how to use this chart. Okay, let's go back to our whiteboard here. All right, so hopefully now you guys know that, you know, the mass of the Earth is the number that goes in here. The distance from the Earth to the moon is the number that goes here. So when you plug out the numbers, you're going to get some number as your answer. And so that is what I'm going to call G due solely to the Earth, as if the sun is not there. Okay, then we need to go back and we need to do this a second time, where this time we are going to pretend that the Earth is not there. We're going to pretend that the only objects that we need to deal with are the moon and the sun. And so we're going to do this again. So then this time, we're going to call this GS, and by this one, we'll call that G Earth. Okay, so that's big G. This time, the mass that goes in there is the mass of the sun, which you can get from the problem. Now, the distance, what are we going to put in for the distance there? Well, hopefully you guys realize that as the moon goes around the Earth, there are times when it's a little closer to the sun than the Earth is, and there are times when it's a little further from the sun than the Earth is. But on average, the distance from the moon to the sun is going to be the same as the distance from the Earth to the sun. So the same number that we plugged in up there, oops, not sorry, that's the distance from the moon to the Earth. Forget that. Okay, so we'll just have to look in the chart and find out what is the distance from the Earth to the sun. All right, so when we do that, we're going to get some other number, and we're going to call that G of the sun. Now, in part A of the problem, they just want you to take the ratio. So if you take the number that you get for G of the sun and you get it divided by what you got for G of the Earth, that will be the answer. Now, the way they worded the problem, you could have done it the other way. I mean, they didn't, at least when I look at it, it's not obvious to me that they specified which one goes on top. So if you decided to take G of the Earth divided by G of the sun, you're going to get a different number. But you know, the way they worded the problem, I would accept either one. So if you If you look here, okay. Okay, so you can see that in the book, the answer book, they had it as 2.3. So if your number is 1 divided by 2.3, I would accept it because they didn't really specify clearly what they wanted. Okay, now, some people are surprised by this. So this number here, this is g of the sun divided by g of the earth. What that means is that the sun is pulling on the moon twice as hard as the earth is pulling on the moon. And a lot of people are surprised when they see that. So they say, well, then why doesn't the sun steal the moon away from us? Well, it's because the sun is also pulling on us at the same time. So so both the moon and the earth are in free fall around the sun. Now, this is something that I think is worth taking a little time to talk about. I'll come back, I'll cover part B in a few minutes. Don't worry, I will get it. But I think it's worth making sure that you guys understand what is free fall and why the moon doesn't get stolen away from us. And the best way to understand that is to think about the International Space Station going around the Earth. Okay, so here is the International Space Station. Those are some solar panels on it. Okay. If you were to calculate what is the value of little g at the position of the International Space Station, you will find that the acceleration due to gravity, or if you wanted to think of the force due to gravity, is almost the same as it is on the surface of the Earth. This picture is not to scale. The distance, the altitude of the satellite above the Earth is actually a very small fraction of that distance. So it is less than 9.8, but not very much. Okay. The gravity is pulling on the satellite and pulling on the astronauts in the space station almost as hard as it's pulling on us. And yet, whenever you look at video of the astronauts in the International Space Station, you see that they're floating weightless. So why are they floating weightless if the gravity that's acting on them is almost as strong as the gravity that's acting on us here on the surface of the Earth? Well, it's because they are in what we call free fall. What that means is they actually are falling toward the Earth, but they never hit the Earth because they are moving so darn fast. Their velocity is such a huge number that, so if you look at Newton's first law, it says an object in motion wants to remain in motion in a straight line. Okay, so this is what inertia wants for them to do, but they don't do that because they are falling. It's just that they're traveling so fast that the Earth is falling away underneath their feet at the same rate that they are falling from the path that they would go if it weren't for gravity. So they are in fact falling. That's why they float weightless. Okay, so we call this free fall. Well, the Earth and the Moon are the same way. It is true that the sun is pulling harder on the Moon than the Earth is, and so the Moon is falling toward the sun, but the sun is also pulling on the Earth really hard, and so the Earth is also falling into the sun, toward the sun. But we never hit the sun because we're going so fast that the surface of the sun falls away under our feet. So we're in free fall. Okay, so that's worth, I think, spending a little bit of time talking about. Okay, now let's go back to this problem here. So for part B of problem 15, what we need to do is we need to recognize that this G value that we've been talking about, that's the magnitude of a vector. So G is actually a vector. It has direction as well as magnitude. So if we were to draw the G field that is due to the Earth, well, that would look like this. That would be the G field at the position where the moon is located. That's the magnitude and the direction of the G field that is from the Earth. But at the same time, we've got the G of the sun, which is pointing off in that direction. And G of the sun is more than twice as, the magnitude is more twice as much. Okay, so in part B, what we need to do is we need to add these two vectors. And we have to recognize that they are pointing at 90 degrees to each other. So be careful. Don't make the mistake that so many students make. So many students, I see them, even at this late day in the school year, what they do is they draw that red line that I've got right there, and they say that's the vector. Well, in this case, the magnitude that they get will be the right number, but the direction is wrong, okay? When you're adding vectors, think of it the way that sailors think of it, okay? So you can slide the vectors around anywhere you want, but you can't change the length and you can't change the direction. But other than that, you can slide them around wherever you want. And so what you should do is approach this the way that a sailor does. So draw one of the vectors. So that's my GS vector. And then even though technically both of the vectors are acting at the same point, so what you see over here, that is a better way to represent what's happening. But when you add them, don't represent them that way. Draw the one vector, and then wherever that vector stops, that's when you start drawing the second vector. So that's G of the Earth. And so your answer vector is the vector that starts where they started, ends where they ended, and doesn't care what happened in between. So the magnitude that we get will in fact be the same as the magnitude that people mistakenly get when they do it like that, okay? But the direction is different. All right, so how do we find out the magnitude of that vector? Well, just do the square root of GS squared plus GE squared. That'll tell you the magnitude. And then if you want to know the direction, which you really should, because technically you haven't completely answered the question if you don't calculate the direction. So to get the direction, just do the inverse tangent of GS over GE, okay? Now, when I looked in the book, when I looked in the answer book that I have, I noticed that they didn't bother calculating the direction. They just calculated the magnitude, which actually kind of surprised me. But that's what they did, so that's all I put here. Okay, now I see Austin is asking a question. Why is GS going to the side if the sun is diagonally down? Thank you for asking that. That is important. Let me go back to this here. Okay, so this picture is so cluttered that it's pretty much useless. Let's draw a new picture here. Okay, so here's the sun. Here's the earth. Here's the moon. So if I were to draw a line from the moon to the sun, it looks like this, but this distance is not to scale. The sun is actually so far away, it's way over here, way over there, that if I were to actually draw it correctly, what would happen is that the line from the moon to the sun would be almost parallel to this lower line here, but not quite. This angle here would be almost 90 degrees, but not quite. Actually, it would be like 89.99999 and probably a couple more nines. So that angle is not exactly 90 degrees, but it's so darn close that we can treat it as if it is 90 degrees. And so that's the answer to your question there, Austin. Hopefully that answers that. Okay, so let's go back here. All right, so here are the answers again. So hopefully you're good on problem number 15 now. The other question that you guys had was problem number 94, and that is a really good problem. I think that's definitely well worth spending some time talking about. So let me open up yet another whiteboard. And here, maybe I'll just clear this one out. Okay, so if I were to draw a picture of the Earth, And here's the North Pole. And here's the South Pole. And here's the equator. And here's someone standing on the equator. All right, now the Earth is spinning. Hopefully you can realize that if the Earth were to spin really, really, really fast, this person would get flung off into outer space because of something that the person would be tempted to call centrifugal force. Now, someone on the outside looking in, they would say, well, it's not really a force, it's really just inertia doing what inertia does. But the person on the Earth, I mean, boy, it sure feels like a real force to them, okay? So our job is to find out what is the velocity, the maximum velocity. Well, actually, let's not call it maximum velocity. We want to know what is the velocity that the Earth needs to have so that we're just short of throwing the person off, okay? The Earth is spinning so fast that the person is feeling no gravity. This centrifugal force, which some of you are going to say isn't really a force, okay? But I would argue that we can treat it sometimes as if it is really a force, is going to be equal to the force of gravity holding the person on there. Now, remember the James Bond exercise that we did a while back? I think this would be a good time to go back and review that. So hopefully you guys recognize this little cartoon frame. So we got James Bond strapped to a centrifuge. Dr. Evil says, when I throw this lever, centrifugal force is going to crush every bone in your body. And James Bond says, there's no such thing as centrifugal force. And Dr. Evil says something that's very important that we talked about last time, but I think it's good talking about again. So Dr. Evil's response is that there actually is. He says that this thing, this claim that there's no centrifugal force, he says, a laughable claim, Mr. Bond, perpetrated by overzealous teachers of science. Simply construct Newton's laws in a rotating system and you will see centrifugal force term appear as plain as day. Dr. Evil is not wrong, okay? If James Bond had been born on the centrifuge and raised on the centrifuge and lived his entire life on the centrifuge, and now I'm assuming that the centrifuge is turning at a slow speed, so it's not crushing him. So think of it as if he's that astronaut in the spaceship. Remember that video that I played where the astronaut was jogging on the walls of the spaceship? That's exactly that. That's like James Bond in the centrifuge. So if that astronaut had been born and lived his entire life inside that rotating spaceship, he would feel a force that pushes him toward the edge here. So here is the rotating spaceship or the centrifuge. Okay. So when the astronaut is standing right here, he feels a force that pushes him that way. Sorry about that. Okay, when the astronaut is here, he feels a force pushing him that way. When the astronaut is here, he feels a force pushing him that way. Okay. Now, someone on the outside of the spaceship looking in is going to say that what he's feeling isn't really a force. It's really just inertia doing what inertia does. But to the astronaut, what he's experiencing is very, very real. And so if he were to take Dr. Evil's advice here, if he were to do what Dr. Evil says right here, he says, construct Newton's laws in a rotating system. Okay, well, this is, here's what he means. Okay, so you guys have heard me say many, many times that you can define the origin anywhere you want, and it doesn't matter, you'll get the same answer in the end. Well, you can also make your origin be rotating if you want. Okay, so what you can do is you can define your origin to be the center of the centrifuge, and you can define your X and Y coordinates like this, where your X and Y coordinates are rotating. Okay, now, if you were the person that was inside the spaceship, you would disagree that they was rotating. You would look out the window and you would say that the spaceship isn't rotating, it's the stars around you that are rotating. So you could define your coordinate system this way. And so if that was the case, this force that you feel that always pushes you toward the wall, no matter where the wall is, if the wall is up here, it pushes you that way, it's over here. That force that you experience from your perspective with the way you've defined your origin, that is a very real force to you. Now, to someone on the outside looking in, they would say it's not. It's really just inertia doing what inertia does. But from your point of view, with the way you've defined your coordinate system, to you, that's a real force. And so that's why Dr. Evil can get away with saying what he's saying. Now, why do I take all this time to explain that? Because when you do certain problems in physics, sometimes it's easier to put yourself inside the space station with the rotating coordinate system. And it's easier to think of centrifugal force as if it is a real force. And the magnitude of that centrifugal force is going to be mv squared over r, where v is the velocity that the space station is rotating at if you're the person on the outside looking in. Or if you're the person on the inside looking out, you don't think you're moving, but you think that the world around you is moving. So the v then would be the speed that the world around you is moving. So you can, in some case, well, you can always treat centrifugal force as if it was a real force. And sometimes that makes the mathematics a whole lot easier. Okay, so with that being said now, let's go back and let's look at problem number 94. And let's solve it both ways. Let's solve it assuming that we treat centrifugal force as if it's a real force. And then let's go back and let's solve it a second time, where the second time we assume we're on the outside looking in, where centrifugal force is not a real force. Okay, so let's do it the first way, where we treat it as if centrifugal force is a real force. So we do it, so we define our origin so that our origin is rotating. The person who's rotating with it, they claim that they are not moving. All right, so when the person inside the system does sigma F equals ma, they are going to claim that they are not moving. So they're going to say that the acceleration is 0. But they're going to say that the force of gravity is or force of centripetal force is a real force. So if we look at the force there, we're going to have mg holding them that way, and we're going to have the centrifugal force going the opposite direction. Now, one of them needs to be minus. I don't really care which one is minus. So mv squared over r equals 0. That's supposed to be a 0. So what you get then is mg equals mv squared over r. Notice the m's cancel. So we get v equals the square root of r times g. So that right there is that would be the velocity where the centrifugal force is exactly balanced by the gravitational force. And so the person in that case would be floating weightless. If the velocity is anything greater, then the centrifugal force will be more than the gravitational force. And so if v is anything greater than this, then that person's going to get flung off into outer space. Okay, so this is the way that we do it if we treat centrifugal force as if it was a real force. Now, let's also do it the other way. Okay, let's do it from the perspective of we are on the outside looking in. And so then we say, well, there is no such thing as centrifugal force if you're on the outside looking in. Okay, so we get rid of the centrifugal force. So the only force that we can see if we're on the outside looking in, well, that's the force of gravity, and that's it. There is no other force. So when we do sigma F equals ma, which is what the person did before, we only have mg. We don't have any other force. But the thing that's different is that if we're on the outside looking in, we say that this person is not at rest. This person is accelerating. And so what's the acceleration if you're moving in a circle at constant speed? V squared over r. So mg equals mv squared over r. So the m's cancel, take the square root, and guess what you get? You get the exact same answer. Okay. So hopefully now you guys believe me when I tell you that in physics, you can define your origin anywhere you want. And you can even define your origin to be rotating if you want, provided you are really careful. If you have a rotating coordinate system, then you got to be super careful, because then the laws of physics are a little different. Then centrifugal force becomes a real force, which you must include. Okay, so the safest way to do it is always do it from the perspective of being a person on the outside looking in, and that way centrifugal force is not a real force. Okay. But there are cases where it's easier to do it the other way. Like, for instance, in the practice test, one problem that we're going to be talking about in just a minute. This problem turns out to be a lot easier to solve if you treat centrifugal force as if it was a real force. Okay, all right, so Austin is saying, well, you're not finished, Mr. Hendricks, because we need to calculate the period. So thank you for reminding me of that, Austin. So let's go ahead and finish it now. Okay, so we know what the velocity is, but the problem is asking us what is the period. So in other words, how much time does it take from one sunrise until the next time we see the sunrise? Okay, so if you have a circle, you know the circumference of the circle is 2 pi r. So if the Earth spins completely around one time, then the distance that it has traveled is, that this person on the surface has traveled, is 2 pi r. So if we use our good old equation, distance equals velocity times time, or distance equals rate times time, if you want to think of it that way. So if you go all the way around the circle, the distance you've gone is 2 pi times the radius of the Earth. Okay. And so that's equal to the velocity that you're traveling at, which is this, times the period, because that's the definition of period. The amount of time that it takes to go all the way around once, that is the period. Okay, so the period is 2 pi r divided by v, which means, let's see, let me clear some space up here. Okay, so the period then is 2 pi times the radius of the Earth divided by v, but v is this. So it means the period is 2 pi times the radius of the Earth divided by the square root of the radius of the Earth times little g. So put the numbers into that equation and you will get an answer out. But be warned, if we're putting in the numbers using standard physics units, the answer that comes out will be in standard physics units. What is the standard physics unit for time? It's seconds. Okay, so the number that we get out of this equation is going to be the number of seconds. Now, the number that I gave you on this sheet right here, okay, when the author wrote up the answer book, they decided that they wanted to put it in minutes. Okay, so that what they did was they took the answer that came out of that equation that you were just looking at, and then so they converted that from seconds into minutes. So they divided it by 60. And now, why did they put it in minutes instead of seconds? Well, maybe just because they thought that you could relate to it better. Because 84 minutes, that's, you look at that and say, oh, that's about an hour and a half. So what that means is, if you look out the window and you see the sunrise, okay, if the Earth is spinning this fast, you would see the sunrise again 84 minutes later. Okay. All right, I think that's all we really should spend time on the homework there. Everybody, you're okay with that? Austin, did I answer your questions okay? And by the way, thank you for asking those. That's important. Okay, So with the time that remains, I want to spend the rest of it talking about the practice test. So let's first look on Canvas, and let's go into the modules here. And then if you scroll down to the bottom here, you'll see three things on Canvas that maybe you didn't see before. Okay, one is I have a link here that is for the midterm exam. Now I haven't actually put anything in there yet. It's just a placeholder right now, but this is where you will click next Monday, or if you're watching the recording here, if you're in the beta class, it'll be Tuesday. So this is where you will click to take the test. If you click on it right now, you'll find out that it's locked and you won't be able to get in. This file that you see right here, this will take you to a copy of the practice test that does not have the answers written on it. It's just the questions only. And this is the one that I recommend that you start with. Don't look at the answers until after you have worked through the problems on your own, okay? And then if you get stuck, okay, then look at the answers, but try it on your own first, okay? All right, so this link right here, this is the one that has the answers on it. So if you click on this link right here, it will take you to this file that you see right here. And what I've done is the same thing that I've done with all of the previous tests this year. The practice test that I'm giving you is the same practice test that I gave to my students in previous years before we had to deal with coronavirus. And so back then, the way I did my tests, are you not seeing it? Hang on, somebody, you still see Canvas. Thank you. Okay, let me go and do a reshare here. Okay, so are you seeing, so you should be seeing the something up at the top now. It says answer key. So are you seeing that now? Okay, good. All right. So this is the reference sheet that I gave all of my students in previous years. It's just a photocopy of that page that I keep telling you guys I want you guys to get familiar with. Except down at the bottom here, I also threw in a couple extra equations. So in all of my previous tests, they always came in two parts. Part one, no calculators allowed and no notes allowed. Part two, yes calculator, yes notes. Except this reference sheet that you see up here, that is something that I did allow them to use on both parts of the test. Okay, so that's the reason why you see it in there. Now you guys understand that when you take the test, there's only going to be one part, and you are allowed to use your notes on the entire part, just like all of our previous tests. Okay, so question number one is, I think, a very interesting one. If you throw a ball, what is the shape of that ball's path going to be? And you see I have a couple of choices here. And I've circled two of them because it depends on how hard you throw that ball. Okay, so if you or I were to throw the ball, that ball is not going to go out into Earth's orbit. There's no way that we can throw a ball fast enough that goes out into Earth's orbit. But if Superman were to throw the ball, that ball could in fact go out into Earth's orbit. So if this is the Earth, and here's Superman, and Superman throws the ball, that ball is going to go out into space, and then it's going to come back. And so what is the path of the ball going to be? Well, it's going to be an ellipse. But you and I, we can't throw the ball that fast. So if I look out my window right now, if I throw the ball, the ground outside my window, it looks pretty flat. And so if I throw the ball, the path of the ball is going to look like this. And that path is going to be a parabola. Now, some of you say, well, why is it a parabola one time and an ellipse another time? Well, because if the Earth could be considered to be flat, if I do a free body diagram, what I'm going to see here is that the force vectors are always going to be straight down. So in this case, what I'm going to get is a parabola. as the shape of the curve. But if Superman throws the ball, he throws it out so much that you cannot treat the Earth as being flat. So if I do a free body diagram, here's the force of gravity is there like that. And here you can see the force of gravity is different. And here you can see the force of gravity is different still. And so in this case, it's going to be an ellipse. Okay. So it really truly is an ellipse. Even when I throw it, it actually is an ellipse. But because the Earth is so big compared to the region that I'm looking at, it turns out that treating it as a parabola is an easier way to do it. Okay, so let's go back to the practice test. Okay, so problem number 2 is just testing to see, do you know how to use the law of universal gravitation? So I'm not going to talk about that. Question number 3 is something that we've already talked about, but it's worth just going over real quickly. So the question says that you're in a car going around a curve really fast, and the passenger says, hey, the centrifugal force is bothering me. And the driver says, there's no such thing as centrifugal force. Well, we just spent the last few minutes talking about that, right? So if you're on the outside looking in, there is no centrifugal force. That force that the passenger thinks they're feeling, that's just inertia doing what inertia does. It's not really a force from the outside looking in. But if you define your coordinate system so that you're on the inside and that's spinning, then to you, that is a real force. Okay, question number 4 and 5. Those are just vector addition problems. Make sure that you guys are good at vector addition. I guarantee there will be at least one problem on the test that's a vector addition problem. Make sure you know how to do that. Question number 6 is just designed to see, do you know how to take a funky vector and break it up into its components? So I'm not going to take any time working on that one. Question number 7. This is something that I required my previous students to memorize. Now, as you guys hopefully know, I'm not really big on memorization. I don't want you guys to memorize lots of stuff, but there are a few things that you should memorize. And the formula for centripetal acceleration, yeah, that's one of the things you really should have that memorized. Okay. And then the direction for acceleration, the direction for centripetal acceleration, well, that's what centripetal means. It means toward the center of the circle. So wherever you are on the circle, if you're right here, the centripetal acceleration is like that. If you're over here, it's like that. It always points toward the center of the circle. The magnitude of the centripetal acceleration is always going to be v squared over r, but the direction changes there, depending on where you are. Okay, Kepler's 3 laws. That's another thing that you guys really should memorize. Now, for the test, obviously you don't have to. You can write them down, okay? But really you should. You should know from memory what are Kepler's 3 laws. You should also know what are Newton's 3 laws. And you should also know Newton's 4th law, which nobody calls it the 4th law, nobody that I know, but it's Newton's law of universal gravitation, okay? Right here. That's something that you should not have to look up on a cheat sheet. You should have that memorized. Question 11 is pretty straightforward, so I'm going to skip that. Question number 12, the whole idea for question number 12 was just to see, do you know how to use this reference sheet at the back of your book? Do you know where to look to find out the average distance of a planet from the sun? In other words, do you realize that the thing you should look for is semi-major axis? That's the whole purpose of that. Question number 13 is worth spending a little bit of time about, 13 and 14 together. Okay, this is something that if you go on and you take physics anywhere else, I can guarantee that you will at some point be asked a question that's basically the same as questions 13 or 14. So what we're saying in this problem is we're saying, let's say that you have 2 objects that are gravitationally attracted to each other. And if you double one of the masses, what happens to the force? The way to answer all of these types of problems is you say, okay, well, what have we got here? We've got 2 objects that are gravitationally attracted. So then you say to yourself, well, what equation governs the behavior in that case. And so you say, well, hey, it's this equation right here. It's Newton's law of universal gravitation. So once you've got that, then you can say, okay, so we're going to double one of the masses. So like M1 here, we're going to replace M1 with a new number that's 2 times what it used to be. So what's that going to do to the force? Well, if you look at the equation, you can see it's not M1 squared. It's not the square root of M1. It's just M1. Okay, so that means if you double M1, then the force is going to be double. If you triple M1, then the force is going to be triple. Okay, so the force is proportional to the mass. Okay, and it doesn't matter which mass you do. You can do either one of them. Okay, now in question number 14, it says that we're interested in the distance. What happens if we triple the distance? Well, again, what you do is you look at the equation and you say, where does distance appear in the equation? So the first thing you notice is that distance appears down in the bottom part of the fraction, not the top part of the fraction. So that tells you that if you make the distance bigger, the force is going to get smaller. Okay, but you'll notice that it's an r squared. So what that means is if you double the distance, the force is not going to go down to 1/2. The force is going to go down to 1/4 of what it used to be. Okay, and what if you triple the distance? Well, the force is not going to go to 1/3. The force is going to go to 1/9 of what it used to be. Okay, so these types of things are very common questions that you see on physics tests. Make sure you understand. The key is just look at what they're asking about. So they're asking about objects that are gravitationally attracted to each other, and then ask yourself, okay, which equation applies? And then just look at the thing they're asking about and see where does that fit in the equation? Does it come in with a m or does it come in with an m squared? Does it come in on the top or does it come in on the bottom? Okay, that's the way to do all of these. Okay, question number 15. Okay, that's just plug and chug. 16, 17, 18, these are all just plug and chug equations. So as long as you know what equation to put the formulas into, okay, that's all I'm after there. Okay, question number 19. Pretty straightforward. We got a runner going around a circle. And so if they're running at constant speed, are they accelerating? Yes. How do you calculate a number for the acceleration? Well, v²/r. What's the direction of the acceleration toward the center circle? This is all pretty straightforward stuff. I don't think I need to spend time talking about this. Problems 20 and 21, those are important ones. And it's been a couple of weeks now since we talked about projectile motion problems. So it's probably good to spend a few minutes talking about them again. If you understand how to approach projectile motion problems, they are really easy. But I've learned over the years that even though we've talked about it a lot, I'm willing to bet that there are still lots of you who still are a little iffy on this. So let's talk about it. And so in problem number 20, what we've got is a car that's going horizontally off a cliff. So there we go. So the problem comes over here and it hits. And so we want to know, something about the car. So we recognize that this is an evil problem. And so who do we call? Well, we call the good twin. And if the good twin does her job right, the ball that she drops will hit the ground at the same time as the evil twin's ball hits the ground. And when the ball hits the ground, or right in the instant right before it hits the ground, it will be moving at a velocity that will be the same as the vertical component of what the evil twin does. Okay, and the same thing over here in problem number 21, the evil twin, instead of the initial velocity being horizontal, this time the initial velocity is up at an angle. So how do we solve these types of problems? Okay, you need to be very, very clear on how we do this. Okay, so let's pick a problem here. Okay, so the evil twin is throwing a ball or shooting a cannon or something with some initial velocity at some angle above the horizon. Okay, and there's a lot of ways that I could do this. I could ask you, how high does the ball go? I could ask you, how far does the ball go? I could ask you, what is the final velocity of the ball right before it hits the ground? Okay. The approach is the same. What we do is we recognize that this is an evil problem. And the reason it's evil is because it's two-dimensional. So what we do then is we call in the good twin. And so the good twin is going to throw her ball at the same time that the evil twin throws her ball. And if the good twin does her job right, her ball will go to the same height that the evil twin's ball does. Her ball will hit the ground at the same time that the evil twin's ball does. And when her ball hits the ground, it'll hit the ball, or in the instant right before it hits the ground, it'll have a velocity that will be the same as the vertical component of the evil twin's ball. But, and this is the big but here, it will only work if the good twin does her job right. So let's see, who should I pick on here? Amy, can you unmute yourself and tell me what does the good twin have to do in order to do her job right?
I don't know if I should give a serious answer or the thing that came to my mind first.
Give me the thing that came to your mind first.
Defeat the evil twin.
Okay, good. I like that. Okay, now give me the
Now,
actual.
if you want a serious answer, that's a great question.
Okay. Okay, so let's suppose that the evil twin is throwing her ball at 21 meters per second. Does that mean that the good twin should also throw her ball at 21 meters per second? Amy?
No.
No.
Okay, so I'm asking Amy here. All right, so Amy is correct in saying no. So how could I calculate how fast the good twin should throw her ball in order for her to be doing her job right? Any idea there, Amy?
Not really. Oh, crap. I need my notes.
Okay, all right. How about Cindy? Cindy, can you unmute yourself and tell us? How would we calculate the speed that the good twin needs to throw her ball at? Worth calling Cindy. Come in, Cindy. Are you there, Cindy? You're not going to admit it if you are, huh? Okay. How about Dylan? Can you unmute yourself?
Yeah, so we're looking for how much the good twin has to throw the ball up, right?
Yeah, what speed does the good twin throw her ball at? So Amy has correctly said that she does not want to match the velocity of the evil twin. If the evil twin throws her ball at 21 meters per second, the good twin does not want to throw it at 21.
What's the angle down there? I can't quite read it. Is it 70?
I didn't put a number. I just called it theta.
Oh, okay.
If you want,
okay.
I can put a number on it if you want. Let's say that it's 53 degrees.
All right. So wait, would it be? Forget. You would want it to be. Give me a second.
Okay, well, I'll tell you what, we're short for time. Calvin has typed.
I think it's.
Yeah, Calvin has typed it into the chat box here. What Calvin said, and it looks like Will and Gia they all agree that the good twin needs to match the vertical component of what the evil twin is doing.
Yeah,
that is the key.
Which would be the sine.
Well, it's the evil twin's velocity times the sine. Don't forget that. It's not just the sine by itself. Okay, so if we break this up into its components, so the vertical component there is going to be V naught times the sine of theta. Okay, so in this case, it's going to be 21 times the sine of 53. Okay, but just remember it as V naught sine theta. That is what the good twin needs to do. If she does that, then the ball she throws will go the same height as the evil twin, and all those other things that I said, but only if she does her job right. And this is how she does her job right. Okay. So make sure that you all understand that. And clearly I can see that a lot of you don't understand that. So it's a darn good thing we're talking about this. Okay. Now, what if I wanted to know how far does the ball go before it hits the ground? So I'm interested in knowing this distance right here. So I'm going to need to know what is the horizontal component of the velocity, which is going to be V naught times the cosine of theta. Okay. So remember how we do this? So first off, we let the vertical good twin help us, and we calculate how much time does it take before the ball hits the ground. Once we know that, then we know that in the horizontal direction, it's as if the good twin were to get in a car, and the good twin drives the car, and she leaves at the same time that the evil twin throws her ball. And if she does her job right, her car will always be directly underneath the evil twin's ball. And so when it gets over here, the ball will go thunk right on top of her car. But what does it mean for her to do her job right? She needs to match the horizontal component of what the evil twin is doing. So then we can use dirt, D equals RT. So if she drives her car at a speed where the speed that she's driving at is equal to the horizontal component of the evil twin, and then we get the time from the good twin over here, then that tells us how far it went. So this is the key to solving all of these problems. If you understand this approach, then projectile motion problems are not that difficult. But if you don't understand this approach, then projectile motion problems become impossibly difficult. So make sure that you guys understand the approach. So in problems 20 and 21, I've got some examples here. So work through these examples and you should be good. Problem number 22 is just a vector addition problem. 23 is also another vector addition problem. Number 24 is just using Kepler's third law. This should be straightforward. Question number 25 is worth spending a minute talking about. Okay. So what we've got here is we got the military wants to launch a satellite into outer space, and they hope that it'll be a circular orbit. Okay. And so this is the velocity that they gave the satellite when it has this altitude. So then the question is, did they achieve their goal? Is this going to give them a circular orbit or is it not? Well, the way to approach this is to remember what is the equation for what I like to call the critical velocity. So right here, this is the equation for the critical velocity. So if the velocity is equal to VC, then the orbit will be a circular orbit. However, if the velocity is greater than VC, then it will not be a circular orbit, it'll be an elliptical orbit, okay? Which the military might be a little bit unhappy about that, but at least the satellite will be in a stable orbit, okay? The big problem occurs, what if the velocity is less than the critical velocity? Well, that's the worst possible case, because then that satellite is not going to stay in orbit. That satellite is going to crash into the Earth, okay? All right, so what you need to do in order to solve this problem is you need to basically just put in the numbers here. So the number for big G, well, you know that, okay? The number for M, that's not the mass of the satellite, that's the mass of the planet that the Earth is orbiting around. So you should get this from the table, okay? Now, the thing that gives students problems in previous years is I always see a student who wants to take this number here and they want to plug that number in for R. Bzzzt. Okay. You need to remember that R is the distance from the center of the planet to the satellite. So if this is the satellite up here, going around like that, okay, it has to be the distance from the center of the planet to the satellite. So when you read the problem here, you'll see it says that this 441,000 numbers, that is above the Earth's surface. So that's the distance from here to there. We need the total distance. So what do we have to do? Well, we have to look in the table to find out what is the radius of the Earth, which turns out to be this number. We have to add that to this number. And so the sum of these two numbers, that's what we have to plug in for R. So every year I give a problem like this, and every year people get it wrong because they forget that this number has to be the number from the center of the Earth, not the number above the Earth's surface. So be careful about that. Okay, so on this problem here, when you put in all the numbers and do the math, you'll come up with this number right here. So this is VC. You look at the number that the military has and they say, uh-oh, we got a problem because the velocity is less than VC. So that means this orbit is not going to be a stable orbit. That satellite is going to come crashing into the Earth. Rats. Okay, so you see how this works, guys? All right, so let's move on. Problem number 26 is just using Newton's law of universal gravitation. Nothing to talk about there. Problem number 27 is worth talking about here. Problem number 27 is about, there used to be a ride at Lagoon way back when I was your guys' age, and it was a really cool ride. It was a big, huge cylinder, and it had a door in it. So you'd open up the door, and when you start off, the floor is up here. So you walk in the door and everybody stands around the edges of the cylinder, and then the cylinder starts to, then they close the door, and then the cylinder starts to spin. And then once the cylinder gets spinning up, then they lower the floor down. And all of the people inside, they get stuck against the wall and they don't go moving down. Now, I've been told that occasionally at the state fair, they have a ride like this that they bring in. Lagoon doesn't have it anymore, but I've been told that they have it at the state fair. Have any of you guys ridden on a thing like this, either at the state fair or somewhere else? Great big cylinder, you go in and it spins. And okay, so I see some of you have. So it's a kind of a cool ride, okay? All right, so what I'm asking here in problem number 27 is I want you to calculate how fast that thing needs to be spinning in order for this to work, assuming that I tell you, what is the radius of the cylinder and what is the coefficient of static friction, okay? So if I tell you all of these things, then you should be able to calculate what it works. Okay, so there are two ways that you could solve this problem. One way is you could solve it from the point of view of someone on the outside looking in. And so if you do a free body diagram, then if you're on the outside looking in, then centrifugal force is not a real force. So the free body diagram that you get right here is the free body diagram. And then the equations that you get are shown down here. I don't think I need to go over it because it's written there. Now, you could solve it another way if you wanted. You could do the James Bond trick. You could define your coordinate system so that it's inside the system here and your coordinates are rotating. And if that was the case, then centrifugal force would be a real force. And the magnitude of that centrifugal force would be mv squared over r. And in that case, you could do it and you would get the same answer. I promise you that either way you do it, you will get the same answer. Okay, now we're running short on time, so I'm not going to actually do it anymore, but you see it's all right here. So guys, please, before you look at the answers, try to do it on your own, okay? Question 28 on the practice test. When I first wrote the practice test, I did it in two parts. So what we've got here is we got a car going around a curve going really fast, and we're worried that we're going so fast that we're going to slide off the road. So your job is to calculate what is the maximum speed that you can go without sliding off the road? Where if you go just a little bit faster, you're going to go sliding off. Okay, so in part A, the road is not banked, so it means it's horizontal. So you've done problems like this in your homework assignment. Part A should be relatively straightforward. Now, when I first made up the test, I also included a part B, where in this case, the road was banked at an angle. And when I did the problem, I made a silly mistake. I left out one of the terms that I should have included. And when I did it, the problem wasn't horribly hard. And so I thought I would include that in there. Now you can see I've got all these lines in there right now. The reason I've got all these lines here is because I've decided that I don't want to do that. Because after I made up the test, I went back and I realized that I had made a silly mistake. I'd left out one of the terms there. And when I went back and I redid it with the correct term, now it still is doable, but it adds a level of difficulty to the problem that I got looking at and I said, okay, it's just not worth it. You guys have got enough other things to worry about. So what I decided here is I've decided get rid of part B. Just don't even try part B. Now, having said that, there are some of you in this class who are capable of doing part B. Part B is not impossibly difficult, but don't do it unless you've done all the other problems first, and unless you're really bored. Okay. Okay, problem number 29 is just a derivation. That one should already be in your notes. There's no point in me going over it now. Problem number 30 is also a derivation. Again, no point in me going over it now. Problem number 31 is very similar to problems. In fact, it's identical. Problem number 31 is identical to problems that we've already done. This is where we have a mass on a string and we're spinning it in a circle, okay? But it's hanging down a little bit, so there's a circle, it's hanging down at some angle. So we've already done problems like this. So there are two ways that I could do this problem, okay? One is, well, actually, regardless of whichever way I do the problem, okay, when you work through it, you will get it down to this equation right here. Okay, so now, if I tell you what V is, so if V is given, and I ask you to calculate theta, that's a really difficult problem. It's doable, but you have to use Desmos in order to solve it. Or now it can be solved if you're really good at trig. Some of you who are in the Math 3 honors class, and a few of you who are in the calculus class, you know some trig identities where if you use these trig identities, you could solve this analytically, okay? But it's very difficult. So if I tell you what V is and ask you to calculate theta, that's pretty difficult. If I were to do that, I would only do that as an extra credit problem. However, if I do it the other way around, if I tell you what theta is, so if theta is given and I ask you to calculate V, that is something that would not be an extra credit problem. You guys should be able to do that. Just, plug in theta there, plug it in there, plug it in there, and calculate V. That's something that everybody in this class should be able to do. Now, doing it the other way around, where I tell you what V is and I ask you to calculate theta, okay, that's going to be difficult because theta appears in 3 different places here. But if I give you theta and ask you to calculate V, you guys should all be able to do that. Okay, well, that's it, and we are now out of time. So, well, we do have 2 minutes left. Anybody want to ask a question, or you want to just call it good? So you guys all understand that next time we meet is the real test. Okay. All right. So if you want to go ahead and type bye in the chat box, then I will see you next time. Be prepared for the test. If you do have a question, what I can do is I can turn off the recording. That way you can ask your question without having it be recorded.